All right, I'm doing more real-world problems of linear equations style. So we have David's experiment, and we're given this information here that there's a weight attached to a spring in pounds. And you can see there's 0 pounds, 1 pound, 2 pounds, 3 pounds, and 4 pounds. And we're asked to see what the length of the spring is when we measure it in inches. So we can see that with nothing hanging off of it, no weight on it, it's 11 inches. 1 pound, there's 13 inches. So you can see that the weight of each pound additionally is changing this graph, or changing this table, I should say. And so if we're looking at this, this is increasing by 1 every single time. So 1 more pound is increasing the weight. And then what's happening to the spring's length is it's increasing every time by 2. So the inches are going to be adding 2 to it. So that is going to help me with my slope because it is 2 over 1, or a slope of the rise over the run. And so that is my slope number. So y equals 2x. And then we have that plus 11, and we get the plus 11 because at 0 weight, we have an 11-inch length of that spring. So that's my starting value right here. So that's how the equation comes about. Now, we have to look at what's going on with these x and y values. So the x is always if you're looking at a horizontal graph like this, the x is always the top number and the y is always the bottom one. So I'm just gonna label that right here. So our x value is the weight of the it's attached to the spring in pounds. And the y value is the length of the spring, which is in inches. So you can see that that's already on here. And so we're looking at the numbers and what they mean. We're asked to use that. So the 2 in the slope means that the spring is stretching at a rate of 2 inches for every pound that's added to this spring. And then the 11 is your initial length of the spring with no additional weight in inches. So again, we're looking at these two numbers right here. That's what they are referring to. And then when we go to graph that problem, you can see this is a graph for it. So if I'm making a graph, you can see that we're starting at 11. So what I've got here is this little like squiggly line. If you're not starting off right at 0, like this is still gonna be 0 right here in the corner. But when you're not starting off and you're not being consistent, like this kind of jumps from 0 up to 11, and then it's consistent all the way up this way. You make a little squiggly line like that. That just indicates that you have a bunch of values that would be lower that you just no point in kind of making such a tall graph with. So our first point is at 0 weight, we have 11 inches. Again, length of the spring in inches is labeled here on the y-axis. And then as you can see, if this is 15, this is 11 right here, this is 12, 13, 14, 15, 16, 17, 18, here's 19. And that's where that's where the table values stopped. So that's why we stopped there at 19. We can continue to go on that if we'd like to. So 0 is 11. Then we graph 1. Graphing 1 is at 13. Graphing 2 is at 15. Graphing 3 is up here at 17. Graphing 4, it would be here. 4 should be 19. It's a little off here, but it should be right here at 19. And then I would continue to keep going. So then 5 would be at 21, and so on and so forth. We're asked to write a short description and an explanation of the data table. So in David's science experiment, he starts with an 11-inch long spring. He adds 1 pound of weight each of the four times to the spring. And each time he adds it, he gets 2 inches longer on that spring. So that is basically an overview of how you could use this in the real world with a question where you have to kind of compile all of these pieces of data all into one big document. If you'd like more questions like this, you can find them on my YouTube channel, You Want Algebra. Check these out under the real world scenarios section.